So in this video, I'm going to be going over the experiment source code folder. So this includes the initializer script and the template Simulink diagram primarily. So to get to the experiment source code, we can open MATLAB and go to the Spot 2.0 folder wherever you've stored it, and then navigate to the low-level files, and then go to experiment source code. So as I've mentioned before, anytime you create a new experiment, the contents of this folder are copied into a new folder which has the name of the experiment. In this folder, we have save data, save figures. I'll touch on these a little bit later. This is the library. So this is the DLL and this is the library connected to the stream data executable. So wherever you want to run this executable, you need to have these two files present. So these two files are stored in the phase space folder, which I showed in the previous video. So they're right here. So if you create a new experiment and for some reason these files are not present, you need to copy them in. They do not get auto-generated when you build the stream data. They never change as the nature of an object file and a DLL file. So then we have the GUI files. So inside of GUI fig, if we open this up, it is the actual image or the figure of the GUI. So nothing here really will do anything. So if we close this and we open up, clear the workspace first. If we open up the mat file or the M file, this is the actual GUI code. So this code is pretty messy and pretty long because it is auto-generated. So if you ever want to make changes to the GUI, you need to use MATLAB's guide if you're inexperienced, or you can also just fiddle around with the code. So you type guide, and then you browse and open up the figure file. You can just ignore these warnings right now. And this will give you access to changing whatever you want. So you could, for example, move that around if you wanted to, or add a new button to do whatever you want. So the way this works is once you've placed a new object, so say I add this OK button, or this, not OK, but just a button called a push button. If I double click on the push button, it gives me all of the basic things I need to modify the button, including the name. So if I say, call this test button, and then I close this, now it says test button. Now we want to assign a function to this test button. So I would right click, view callbacks, and I would want it to be what happens when I call this function or press this button. So now if I say I want to do a equals 1 plus 3, and then I want to print that to the command window. I calculated a to b %f dot backslash n, and then we want to give it the variable a, and then we want to save this. So now if I run this GUI, we have our test button up here, and we can just click test button, and we can see I calculated a to be 4. So we've created our very first button. I do not want to save this. I'm going to close that, delete this button, save that, close that. Now, the combined data function I will go over in another video, but basically this is one line of code, and you copy this into the saved data folder, and it will stitch together all of the separate data files that are exported from the Raspberry Pi, because the Raspberry Pi cannot export everything in one file. It's going to export experiment 1 -1 -2 -3 -4 -5. And so in order to get all of those into one file, you just copy the combined data into the same folder as the data and you run it. And it will combine all mat files with the same title, but with different indexes. So I'll give an example of that in another video. And then we have the four most important files here: the initializer, the model parameters, the thruster parameters, and the template. So the easiest ones here, we have open up the model parameters. So when we load that, we have the inertia for black, the black mass, the inertia for red, and the mass for red. So these are pretty self-explanatory. Then we open up the red or the thruster parameters, which contains F thrusters black, F thrusters red, and then thruster distance to CG for black and thruster distance to CG for red. So in here, this is the approximate force for each thruster. So we estimate it to be around 0.25, but depending on how many thrusters are open at once, this could be as low as 0.1, or it could be as high as 0.5. So the other thing in this file is the thruster distance to CG. So this folder, or this mat file variable, contains in millimeters the distance between every thruster and the center of gravity. So this is used in the control mixer. So now we can open up the initializer script. Everything up to this point is just introductions. And here we start defining some user variables. So these are just to convert from degrees to radians and vice versa. This is the x and y length of the table in meters. So this is was measured at one point. And then we have the PID gains for the red and the black platforms. So this is the PD gain for the red X, the PD gain for the red Y, the PD gain for the attitude red. And the same goes for black. We also have the ability to add noise to red and black if we want to. If the phase space is running at 10 Hertz, generally speaking, the noise is basically non-existent. So here we have the base sampling rate. So this is the sampling rate that the template will run at. So this is what the Simulink diagram will actually run at. So here we have it set to 20 Hertz actually. And so if we run this and run the Simulink diagram, we're running it at 20 Hertz. And this is the server rate. So this only gets used in simulation, and it allows us to hold data such that it's representative of what will happen in an experiment. Since in an experiment, we can't send data up at exactly 20 Hertz, so we send it at a half rate, which I went over in the previous video. So in this case, we want it to be 10 Hertz, so we set it to 0.1. So then we have the durations for the experiments. So phase 0, 1, 2, 3, and 4, and 5 represent the different stages of an experiment. So I think here is a good opportunity to actually open up the template and kind of go over the experiment loop. So I'll open up the Simulink diagram, which may take a little bit of time. So basically each one of these is the duration of the phase, not the start time. So if you want the phase 3 experiment to last 131 seconds, you would put 131. And then here, when we say phase 3 end, this will actually automatically calculate the end time for phase 3 based on the duration you set for everything. So we've opened up the Simulink diagram, and we can put this over here and zoom in a little bit. So this is the actual experiment loop. So we can see phase 0 duration. That corresponds to phase 0 here, which is the waiting for synchronization phase. So if we open this up, we can see that we have a subdivision between the red and the black platform. So if we want to look at red, you can see nothing is actually happening. So we're sending 0 force and torque to everything. So this includes the platform and the arm. And if we look at the pucks on-off block, the pucks are off, set to 0. So it's waiting, so it's not floating. So in here we have that set to 10 seconds. So then phase 1 corresponds to the floating phase. So this is when it starts to float before it actually does anything. So here we would expect to see 0 forces to everything and the pucks to be turned on, which is the case. And we have that set to 5 seconds here. Then we have phase 2, which is move to initial position. So if we open this up, we have a PD controller, which sends forces to X and Y and a torque to the attitude in order to basically get to the initial states that we set. So the initial states, init states red 1, 2, and 3, are set in the initializer. These are located at the very bottom in this subsection, where it says set drop initial and home positions for each platform. So these are located here, and they need to be in meters and radians. So then we move on to phase 3. This is where the bulk of any new experiment will happen. Up until phase 2, we shouldn't really be changing anything beyond the duration if we want to. So inside of the red platform and the black platform, we have subphases now. So these are subphases that occur during phase 3. So the duration of each subphase is defined just below the phase duration. So subphase 1 is get to some initial point, which in this case I just set to initial states, but you can make it do whatever you want. Subphase 2 is to stop sending any forces and to defloat the platform, such that when you start up subphase 3, you are starting with 0 initial conditions. This is a good way to check simulation versus experiments, because you know you're starting from the same state. And so in this case, the float should be 1, which it is. And then subphase 4 is when we actually do what we wanted to do. So in this case, I'm basically just telling red to maintain its position. And so each of those subphases is 5 seconds, 5 seconds, 1 second, and then 120 for the final subphase. And so when you put in the phase 3 duration, you have to put this to be the sum of these subphase durations. So make sure that this is correct. Otherwise, you're going to have some strange behavior in experiment. So then we have the 4th phase, which is the return home. So here we have these constants, which are the home states. So these home states are defined, again, at the very bottom here. Home states red, home states black. The units are the same as the initial states. And we have that set to about 20 seconds. So the black has the same thing. Then we have phase 5, which is hold home. So this just holds the home state such that the platform is guaranteed to be at a still position when the puck's turned off. And then phase 6, which has no duration because it's the final phase, is when we stop floating the platform and we spin down the reaction wheel if it is active. So the pucks are 0, the forces are 0, and the reaction wheel is being reduced. So that covers the durations, and this is basically calculating a bunch of parameters using those durations. So we have the full simulation time, the end time for each phase, and the end time for each subphase. Here we load in any required data. So this is what I went over before, which are the model parameters and the thruster parameters. And then here we set the drop initial states and home states for the black and red platforms. Now in experiment, the only thing that gets used are the initial states and the home states. In simulation, the drop states define your starting position. So when you run an experiment, this will change nothing. But if you want to compare simulation to experiment, you generally want to try to make the drop states the same as what you did in real life. And then the very last step is to run the GUI. So that basically covers the initializer. So if I run this, we have our GUI, which I went over in a previous video. But basically, to get a little bit more detail, this, as I said before, this opens up the diagram. This lets you pick the platforms, so red, black, they start here. Then once you've got your simulation diagram all set up and you know your simulation runs well, you would want to deploy the code to red and black. So if you're running an experiment with red and black, you have to click both, and you have to wait after you click one before you click the other one. If you click deploy code red and you immediately click deploy code black, it would technically still work, but it would be buffered, so you'd have to wait a while. So once both platforms have their code deployed, which I'll go over in an experiment demonstration video, the next thing you do is float the platforms. So when you're putting the platforms on the table, make sure that they're floating. Do not put the platforms on the table without having the pucks turned on. And then you want to start the experiment, so you just click start and then stop, and that's it. and this will reset the experiment. So you can start, stop, start, stop as many times as you want. There's no waiting between that. And then once you've run an experiment, you usually want to save the experiment data. And that's basically all the GUI does, really briefly. So now we can start to actually dig into the template a little bit more. So I've gone over the main part, which is the experiment loop. But just to be thorough, here we have the memory store blocks. So you do not want to edit anything that already exists. But basically all this allows you to do is to bring data between if statement blocks. So if you say run a Simulink or run a block system at this level and you get data and you want to send it into, for example, subphase 4, we want it to use the position because it's part of the PID controller. You need to use a memory store block. It's just how it works. So you can add a new memory store block if you want. You can just copy an existing one, give it a name. We'll call it test. And then if you want to retrieve data from this test block, you click on the right arrow, and then you put this wherever you want to retrieve this data from. And then if you want to store data in it, you grab that side. So if I were to feed in a constant 1 here, and then take this test and put it into one of these if statements, I'd be able to actually retrieve that data. So that's all that's there for. In this block, we have the dynamics for the plant. So it checks if this is a simulation. If it is a simulation, then we run the dynamics model. So that's stored in here. So we have the red dynamics and the black dynamics. They're basically identical with a few differences. So for the red platform, we include the torque of the reaction wheel. Then at the output of each of these, we have a sample and hold such that it matches the phase space streaming rate. And then we send these into the memory store blocks for position. We also take the derivative and store that in the velocity block. So this is a special case derivative, which basically takes the derivative in such a way that we don't get spikes if our data sample rate is low. In this little section here, we have some extra resources. So this is the custom derivative block. Anytime you want to take the derivative in this, you have to use the custom derivative block, otherwise you're going to get weird behavior. And then we have calculations for the elbow, wrist, and shoulder joint based on LED positions. On the bottom right, we have the external hardware. So this is where we collect experiment data. So it checks if it's a simulation. If it is not a simulation, then we go into here. Then it checks if we're running red, black, or red plus arm. So any one of those. In which case, we don't need to do anything. We don't need to send this data anywhere. And we can just grab it from our UDP receive block, which I'll go over in a separate video. So we get our UDP receive, we demux it, and then we get our experiment time, position, velocities for red, black, and the arm LED positions. If we are running red and black at the same time, then we need to retrieve everything on red and then send it to black via UDP block, because we can't run two phase space blocks at the same time. On the bottom right here, we have the magnet state. So this is for the electromagnet that was developed for the robotic manipulator. If you change this number to a 1, then it turns on the magnet. That's basically it. In this little box here, we have the log data. So this is where we log any data for experiment and simulations. So if you want to add new data, just create a memory store block, feed in whatever data you want to that memory store block, and then grab the output memory store block and put it into one of these data packets. So right now it's just the time, the saturated forces, and the positions and velocities for the red and black platforms, and this is stored in a data packet. And that's basically all you need to do is store new data. And then in the hardware control block, we have the control mixer for the thrusters. So I'm not going to go over this in too much theory, but basically all this does is it takes your desired force, puts it in the body frame, and then calculates the thruster PWM required to get that thruster force. Now this actually uses or calculates a saturated force. So this ensures that we're not commanding something that we can't actually do. So that's why we get as an output, here, we get the saturated torque and saturated forces. And then this gets sent to the thruster PWM block. So this PWMs all of the 8 thrusters. And that's basically all of the important stuff in the template. Generally speaking, you only want to add stuff to the phase 3 experiment. You can add as many subphases as you want. So if you wanted to add a new subphase, you'd create a new constant in the initializer and call it subphase 5. And then you would click on this and add a new if statement. So if the time is less than U6, which would be our phase 5 end, so we need 6 inputs, and then we'd feed that into the if statement, and then we can copy one of these and just do that and call it subphase 5. And then you can put whatever you want in here and you'll have a 5th subphase. You can just keep doing that as many times as you want, as long as the sum of all of these subphase durations is the same as the phase 3 total duration that you used. So I can close this. And that basically covers it. So in the next video, I'm going to be going over the creation of a custom device driver block. So this will allow you to communicate with external hardware that requires some kind of C code to use, like the Dynamixel actuators.